Before I proceed further with the Schrödinger equation and solve it for different physical problems, let me discuss a few things. First one is stationary states. These states are very much important. I'm coming into that. Why is it important and what are the advantages of having stationary states and what is actually meant by stationary states. First, I would like to start with time dependent Schrödinger equation. Why time dependent? Because this contains an explicit time factor. This psi is a function of both space and time, and here I have a space dependent potential only, because this potential is independent of time. It is dependent entirely on the position or the space. So psi can be written as space part and time part. This is capital psi, this is small psi, and this is phi. Let me make the partial derivative of this capital psi. Why I am writing this as partial derivative? Because psi contains explicit time factor. So as psi is variable of more than psi is dependent on more than one variable, so we need to write it as partial derivative. And why I am writing ddt of phi here? Because it contains ddt means I am taking the time derivative, and phi is dependent explicitly on time only, so I can write it as ddt. Otherwise, if this wave function is dependent on more than one variable, we need to write it as partial derivative. That is the philosophy of taking partial derivatives. Similarly, as this Schrödinger equation, time dependent Schrödinger equation, contains first derivative of time and second derivative of space, so I am doing del psi del t and del 2 psi del x square, and I am getting this one and this one. I am going to substitute these values into equation 1. After substituting, I get, so after substitution, when I got this, I am going to divide it with capital psi, which means I am going to divide it with small psi phi. So now after dividing both sides by small psi phi, that is space part and time part of the wave function, I am getting this. Now equation 2 is a very important one, because the left hand side of the equation is entirely dependent on time explicitly, and the right hand side of the equation 2 is entirely dependent on space part, because I have already taken this potential as dependent on space only. So this is a separation of variable, and the motivation of separation of variable is when I am getting terms like this, that is these terms and these terms, where this term is dependent on only one variable, and this term, this entire right hand side is dependent on only one variable. So I can equate these two terms to another constant E. So left hand side is equal to E. If I solve it, I will get the wave function phi, and similarly right hand side is like this after equating with the constant E. So I am getting equation 4, and this is time independent Schrödinger equation. There is no time factor in equation 4 anywhere. Now I am going to solve equation 3. That is quite easy. I am just following some regular or some very familiar procedure of indefinite integral. So after integrating, left hand side I will get log phi, and right hand side, as I, E and H cross are not dependent on time, so this is treated as constant. I am taking I, E by H cross out of the integration sign. So I am getting integral of t dt is equal to t only, and log c is my constant of integration, as we need this constant of integration for indefinite integrals. So phi t looks like this, because just I am getting this if I have log phi by log c, I will get a minus et over h cross. So phi t is nothing but exponential minus I e t by h cross. So my wave function will take this kind of form where psi x is a space term and this is time dependent term, exponential minus I e t by h cross. This is completely okay because if t is very large, e to the power minus infinity tends to 0, that means the wave function will not blow up. If it is plus, then if t is very large, e to the power plus infinity tends to infinity, the wave function should blow up. So we can take this solution. Mathematically, we can take the solution. Physically, it is completely okay. Now let me define the probability density corresponding to this wave function capital psi. Now probability density is defined as this, and it can be written as psi star psi because psi contains I term, so it's a complex one. So if psi is this one, psi star is exponential plus I e t by h cross, which means if I want to find out psi star psi, time factor cancel out, only left with the space term here. So evaluating the probability density of big psi is basically evaluation of small psi, probability density in the state small psi. Now what do you mean by, what I meant by stationary states is, first we need to find the expectation value, and if this expectation value is constant in time, this expectation value should be calculated in this with this wave function, and with this wave function if it comes out to be constant, then I can call this as stationary states. So my motivation is we need to find out expectation value. If it comes out to be constant in time, the state is called stationary states. Though the state is having an explicit time dependence, but expectation value is what I call the regulating factor in determining whether this is a stationary state or not, whether psi is a stationary state or not. And from the probability density, we can easily see from equation 7 that though big psi is dependent on time, the probability density of this big psi is completely independent of the time factor. So if I want to find out expectation value of a quantity which is dependent on x and p, whatever may be the quantity, it is function of position and momentum, and expectation value means, this is the definition of expectation value. Integration is over the entire space, integration is on the space factor. So here is the quantity A, which is dependent on space and momentum, and expectation value is calculated on small psi, capital psi, because if I make capital psi mod square, I will get just small psi mod square, which means small psi star small psi. So finding the expectation value for this state in equation 6 is basically finding the expectation value for the states for the wave functions small psi. Now let's come to the Hamiltonian. Now as these are stationary states, which means it does not have an explicit time dependence, and stationary states must have a definite energy value, and we know total energy is equal to kinetic energy plus potential energy. Potential operator is by definition written as h cross by I ddx. This is the standard definition of the potential operator. So here if we apply P equal to this, I will get minus h cross square d2x dx square. So for P square, I need to write minus h cross square by twice m. Twice m comes from this So my Hamiltonian, that is the total energy value, becomes this plus this. This gives me the kinetic energy and this gives me the potential energy. So from equation 4 we already written here. If we see equation 4, we can see that this minus h cross square by twice md2 psi dx square plus v is actually the Hamiltonian. So instead of writing the entire term, we can substitute with the operator Hamiltonian, and it is acting on psi, and this is equal to E psi. This is from equation 4, that is time independent Schrödinger equation. Now we need to find out the total energy, the expectation value of this total energy, that is the average value, we can say that, of the total energy for this state. And I will calculate, I will investigate that whether the expectation value for these states of this total energy H is constant in time or not. According to the definition of the expectation value, I am trying to integrate this H for these wave functions, and I am just using the definition of the expectation value from equation 8. And as H psi equal to E psi, so H psi means E psi, E is constant in time, so it can be taken outside the integration. I am left with psi star psi dx. This is nothing but the probability amplitude of psi, and this probability amplitude of psi over the entire space must be equal to 1, because the integration is done over the entire space, and the probability of finding the particle over the entire space is definitely 1. That is, somewhere in the space I should find the particle. Chance of getting the particle, if I look through the entire space, must be equal to 1, which gives me the value of the whole integration 1, and I am left with E only. So expectation value of the average value of this Hamiltonian, the total energy comes out to be E is constant in time, which means I can easily say that the states are stationary states. Variance, sorry for the interruption. What I mean by variance is, suppose I am trying to measure a quantity T for certain state, say psi. Suppose I have measured the value of this quantity as T, but I expect this as this. This is my expectation value and this is what I get. So deviation in T is defined like this, because I am expecting this, I am getting this. If now I can write it as this also, but if I make del T square, I will get T minus expectation value square. So if I write del T as expectation value T minus T, making square of it is the same. So it doesn't matter what I write. I can write T minus expectation value of T or expectation value of T minus T, because I'm going to square of it. Now the variance is, if I make a square root of this entire quantity, which means this one. So variance means what I expect and what I get, square of it and root over of this square. And this is often termed as a standard deviation also. So variance of this value of h, of the quantity h, which is the total energy, is sigma h square, and it is defined as expectation value of h square minus, first I take expectation value of h, then make it a square. We know that expectation value of h is nothing but E, and expectation value of h square is E square. So the variance is 0. What does that means? What is the significance of equation 13? Means if I calculate the energy E for these states, every time I calculate this total energy of the particle, I am certain that I will get a value E. So variation 0 ensures me to get this energy value E for every measurement. Now let's come to the general solution. We know that general solution is actually a linear superposition of different separable solutions. In my wave chapter superposition, I have already shown that if I make a superposition of individual solutions, then I will get the general solutions. So by separation of variable, I get separation of variable of x psi xt, I will get these wave functions which are dependent on x. Time factor is fixed, it is always minus et by h cross, so I am not writing it here. And for every psi value there is an energy value. This is nth psi value, this is nth energy value, and this goes on up to infinity. Now if I take only these two wave functions, psi1, psi2, corresponding these two energy value E1, E2, and make a superposition of psi1 and psi2, I will have a general combination, I will have a combination of this solution psi1, psi2, which will give me a general solution, which is a superposition of psi1 and psi2. Just for example, I am taking, just for the sake of understanding, I am taking only these two solutions. I can take any number, whatever I wish. So for psi1 and psi2, the linear combination will be linear combination of capital psi1 and capital psi2, where capital psi1 contains psi1, capital psi2 contains small psi2, and the time factor is like this. So my general solution will be like equation 14. I have to take all the n values from 1 to infinity. So I am making a summation of all these wave function psi n, all these energy values En, and this is Cn is the coefficient. I am just going to describe what is it. So this is my general solution, which is a linear superposition, that is simple algebraic sum of these individual wave functions. Like if I take example of psi1 and psi2, then only for psi1 and psi2 the general solution capital psi will be psi1 plus psi2, just the algebraic summation. That is the definition of superposition. Now what will these wave coefficients, these are constants, what will the coefficients Cn says to me? Suppose I have 4 wave functions, that is psi1, psi2, psi3, psi 4 corresponding to the energy value E1, E2, E3 and E4. So for the general combination I have to write C1 psi 1. Now comes the time part plus C2 psi 2 e to the power minus I E2t by h cross plus just the algebraic summation C3 psi 3 e to the power minus I and C4 psi 4 e to the power minus I E4t by h cross. Now this significance of this C1, C2, C3, C4 is, this will tell me that in this entire solution, in this summation, how much contribution comes from psi 1. C2 will tell me how much contribution will come from psi 2 and how much contribution comes from psi 3 will be calculated from C3. How much contribution comes from psi 4 will be calculated from C4. Suppose C1 equal to say 50% C1 and 20% from C2 and say 15% from C3 and another 15% from C4, which means that is this is the expectation value. Suppose C1 equal to 50, not the percentage, C1 equal to 50, C2 equal to 20, C3 equal to 15, C4 equal to 15, just for the sake of understanding. So what we mean by that is in the entire solution, in the entire summation, contribution of psi 1 is 50%, contribution of psi 2 is 20%, contribution of psi 3 is 15%, and contribution of psi 4 is another 15%, which will give me 50, 70, then 15, then 15, that means 100%. This is actually what we mean by the evaluating the coefficients. And the boundary condition of the problem, that is the initial conditions of the problem, will be helpful in determining these constants. We'll do that. So what is the summary of this class is or my video is, first I wrote Schrödinger time dependent equation, which looks like this. This tells me that if I know the value of the wave function at t equal to 0, then by solving this equation I can find out the value of the wave function at time t at a subsequent time t, where the potential, where the particle is subjected to a potential Vx, that means the potential is entirely dependent on x space conditions. It is not a time dependent potential. And my first strategy was to solve equation 4, which was time independent Schrödinger equation, which I got from separation of variable of this time dependent Schrödinger equation. So first we need to solve this time independent Schrödinger equation in order to find out the psi x part of the wave function, that is the spatial part of the wave function. Once I get the spatial wave functions like psi 1, psi 2, psi 3, etc., with the energy values E1, E2, E3, etc., I will make a linear combination of the spatial parts, and by applying proper initial condition I will find out the values of the coefficients, and this will give me the general solution capital Psi at a time t equal to 0, that is the initial solution of the equation, initial solution of the Schrödinger time dependent equation. Then I have the time factor e to the power minus I E N T, or rather e to the power I E T by H cross, and just by introducing this solution to this spatial part of the wave function, I will get value of the wave function capital psi at a subsequent time, at a later time, small t. So here, by superposing this, I will get the capital psi. So this means this is nothing but psi n xt. So for each value of n, I will get a value of wave function capital psi, that is capital psi 1, capital psi 2, capital psi 3, etc. for a subsequent time t, and I will get the general solution at a subsequent time small t.